Okay, so short class today. So let's look at what inverses are, taking notes on inverses. So we experienced it today with the patty paper. Let's go over what we already know. We learned this in Algebra 1. When is a relation set of points a function? Let's see if I can zoom in a little. All right. When is it a function? When every x has one and only one y value. All right, what test tells you this? We know that this is the vertical line test. Vertical line test. And what that is if a vertical line drawn through the function crosses a relation more than once, then the relation is not a function. So let's talk about here. So we have power functions with inverses. In general, what power functions have inverses? And what we wanted, the best way to show this is just to draw a little sketch. So let's draw a coordinate plane, xy. What functions, what power, meaning x to what power, generally have inverses? Well, let's draw this function. This is a cubic function. It's odd, right? This would work for a line. Generally speaking, odd powers have inverses, because whenever I draw a vertical line, they only cross through once. We learned today with our patty paper that with inverses, the domain of f of x becomes the range of the inverse function. The range of f of x becomes the domain of the inverse function. So let's do an example. All right, example. If I have f of x is equal to the square root of x minus 3, what does that look like? So first of all, in the little teeny sketch here, I know what that is. That's a root function that shifted right 3. So here at 3, I start my root, and it looks like that. There's my function. Let's think about this function, what the domain and range are. The domain here, what are the x values? Is x is equal to 3 to positive infinity. The range is the lowest y value is 0, including 0, and goes to infinity. So without drawing the inverse function, what do I know? I know that if this is f of x, then if I had the f inverse of x, its domain would be 0 to infinity, right? And its range would be 3 to infinity. Okay, because that's what happens with inverses. We'll see it on a graph, but we know it by principle. All right, let's talk about functions and their inverses. When does a function have an inverse? All right, when does it have an inverse? This is different, okay? When, and this is going to be kind of, you might be predicting this, when every y value, notice I'm putting my finger over here, when every y value has one and only one x value. All right, so when does a function have an inverse? When every y value has only one x value. What could tell me this? And I'm going to tell you, this is the horizontal line test. The horizontal line test tells you if a certain function, if you draw a horizontal line, if a horizontal line crosses a function more than once, then the function's inverse, not the function itself, but the function's inverse is not itself, I'm adding that word, a function. Let me draw a picture because pictures speak louder. So in general, what power functions do not have inverses? Draw your little axis here. And let's look. Let's look at even powered functions. Y equals x squared. So this is y equals x squared. It has an even power. Let's look at it. Itself, it is a function, right? Because it passes the vertical line test. But what about the horizontal line test? This fails the horizontal line test, okay? Because it hits twice. So it fails the horizontal line test. So we know that the inverse of y equals x squared will itself not be a function. And let's just picture it real quick. This, if this is f of x, then this is f inverse of x. Let's just draw it really quick. Teeny little sketch. What's going to happen? It's going to be, this is the inverse function. This is the inverse function itself. Okay? And because that's it's flipped over the y equals x, right? I just flipped it over the y equals x, the origin there, and it fails the vertical line test. So the inverse is not a function. And I knew that because the f of x itself failed the horizontal line test, whereas this function passed the horizontal line test. Okay, it's a lot. So if you have a function like this that's failing the horizontal line test, what can you do to make functions have inverses? And the answer is, write a big, restrict the domain. Okay, so let's draw y equals x squared. So just sketch this in here, the whole thing. All right, 2, 4, negative 2, 4. Okay, I'm sketching my y equals x squared. Now, if I want the inverse of this function to be a function, this is what I do, and I want you to just do it with me with another color. Cross out. I'm going to cross out half of it so that when I flip it, okay, when I flip it, it itself is a function. Because this part of the graph is making it not a function, so I just restrict the domain. And what would I restrict this domain to in the blue? It would be 0 to positive infinity. Now, if I restrict the domain, then this blue function, the inverse of this blue function, is itself a function. Let's look at this problem right here. X, the absolute value of x plus 3. So that's shifted left, right? So we've got here, and then a 1, 1, 2, 2, wow. So 1, 1. So we've got this function, right? It's an absolute value x plus 3, shifted left. To make the inverse of this a function, restrict the domain. And you can restrict either side, okay? So the domain of this function, if I want its inverse to be a function, has to be only negative 3 to positive infinity. I restrict the domain. Now when I flip it, okay, it's going to be like over here. And it will itself be a function. It's going to flip over the line y equals x. I see I mirrored it. I just mirrored it. This is the flip. Not the flip. This is the inverse function. The inverse function is mirrored over the line y equals x. Okay, so just so you can picture that, the line y equals x is here and here. And inverses, remember from Patty paper today, are flipped over that line. Okay, let's finding inverse functions. Today with the graph paper, the Patty paper, we found them experientially. Now we're going to find them algebraically. Here's what we do. We have this function, y equals negative 2x plus 6. To find it algebraically without going through the Patty paper exercise, we write the original. There we go. Switch x and y. So now, switch them. X equals negative 2y plus 6. Switched. Isolate y. Solve for y. Isolate y, okay? Solve for y. So, subtract the 6. X minus 6 equals negative 2y. Divide by negative 2. Divide by negative 2. Negative 2, negative 2. Everything divides by negative 2, and I get y. I've isolated y equals negative 1/2 x plus 3. This is the inverse of this. And this is a superscript there. Y inverse, okay? So this is the inverse, this is the original function. All right, f inverse of x. This is up here, f of x. Sometimes we call it y and y inverse, y little negative 1. All right, let's do it graphically. Let's graph negative 2x. I'm going to graph it in blue. 2x plus 6. So I start with the 6. I put a point at 6, and I'm graphing a negative 2 slope, so I know it's going to be a slope like that. Down 2 over 1, down 2 over 1, down 2 over 1. There's my line. Draw it in. This is my original f of x line. Okay, this is y equals to negative 2x plus 6. Okay, let's just plain graph from the equation the inverse. Has intercepted positive 3. It's also got a negative slope, but it's going to be flatter. So it's going up 1 over, down, let me go down 1 over 2. Down 1 over 2. Up 1, left 2. However, there. Graph a few points. Now, that's just me graphing this equation. Draw it. Different color. This is f inverse of x, which is y equals negative 1/2 x plus 3. Now, I want you to draw the line y equals x. Now, y equals x is just 0, 0, 1, 1, 2, 2, 3, 3, 3, it's so hard to see this, 4, 4. Okay, just graphing the line y equals x. Okay, this is the line y equals x. What do we see? We see the mirror again. All right. So we see it graphically, we can do it algebraically. Now we're going to verify these functions are inverses. You use compositions. All right? So, and here's the definition of an inverse. If f of g of x is equal to g of f of x, and they both equal x, if this is true, then the functions themselves, f of x and g of x, are inverses. So this blue function was f of x, and this function in red is g of x, okay, the inverse. And we're going to verify that f of x and g of x are inverses with compositions. So let's do f of g of x. So here, this is inverse. We're going to call this g of x, okay? Now, So what is f of g of x? All right, well, g of x is here. This is going in here, and here's f of x. So I take my outer function, -2, leave a space for x. There's f of x. And my x value is going to be this whole function. And by the way, I know these are typos. We need to, this function is plus 6. Okay, and what was this? This was -1/2 plus 3. Okay, so that's just a typo there. Sorry about that. All right, those are the inverse functions, and we're going to see if they work. I'm putting in the inverse function, -1/2 x plus 3. And by the way, this was 6. Work it out. Just do the math. When I work this out, I get -2 times -1/2 x is x, right? -2, this just becomes a 1. -2 times +3 is -6 plus 6. These cancel, and my answer is x. So far we check out. Let's see about g of f of x. Well, I know f of x is -2x plus 6. Let's write the outer function, g of x. G of x is -1/2, leave a space for x, plus 3. Plug in your f of x in here, -2x plus 6. This is doing the compositions. Now I'm just going to do the math. Equals -1/2 times 2x is x. -1/2 times +6 is -3 plus 3 equals x. So f of g of x equals x, g of f of x equals x. I have verified that these two are inverses of one another. All right, do it again. Actually, you guys try this. Just like we did here, you try it and check it with me in class tomorrow. But follow the left-hand side. Algebraically find the inverse. Follow these directions. Graph both functions. You have graph that, and then whatever you get, graph that, 2 different colors. Do they mirror over the y equals x line? And then verify with compositions that those two functions are in fact inverses. All right, see you tomorrow.